Hi and hello. My name is Norwadiha and we are from Group B. So we consist of six members, which is Zulhafiz, Amir Rashidi, Balkis, Yazid, and also Nakyuddin, including me. So right now we are going to present about the rocket engine converging-diverging, which is we call also with the Laval nozzle system. So we move on to the next part. Why does the compressible flow matter? Because in the real world, gases don't behave like constant fluids. Their density can change significantly with pressure and also temperature. If we ignore that, our predictions will fall apart. That's why compressible flow analysis is required for accurately predicting pressure, temperature, and also velocity in the system. So it is not optional actually because it is important for designing high-speed engineering system like jet engines, rockets, and anything like high-speed aircraft. So this is also important. Why? First, because we want to improve efficiency and also performance. And the second one is we want to prevent design errors and performance. And the third one is we want to make us enable to predict shockwave in high speed flow. So the engine will not burst.
Explaining about the geometry nozzle. The figure on the left shows the geometry of the lava nozzle, which is widely used in rocket propulsion system. The nozzle consists of five main sections. The first one is combustion chamber to store high pressure and high temperature gas. The second one is converging section to accelerate subsonic flow, and the third one is throat, where the choke flow happens, and we have diverging section to accelerate supersonic flow, and the last one is nozzle exit to produce thrust. After understanding the geometry of the nozzle, let's look at how it works as a complete system. The process begins inside the combustion chamber, where fuel and oxidizer react to produce high pressure and high temperature gases. These gases contain a large amount of thermal energy. As the gases flow through the nozzle, they are continuously accelerated. In the converging section, the subsonic flow gains speed. At the throat, the flow reaches Mach 1, creating a choke flow condition that controls the maximum mass flow rate. Beyond the throat, the gases expand through the divergent section. Here, the thermal energy is converted into kinetic energy, allowing the gases to accelerate to supersonic velocity. Finally, the gases leave the nozzle as a high-speed exhaust jet. According to Newton's third law of motion, the backward expansion of the gases generate an equal and opposite reaction force, producing the thrust that propels the rocket forward. The nozzle achieves its highest efficiency when the exhaust pressure at the nozzle exit is approximately equal to the surrounding atmospheric pressure. After understanding the geometry of the nozzle, let's look at how it works as a
So right
complete.
now, I'll be explaining on the compressible flow behavior of the rocket nozzle. So compressible flow actually occurs when there is changes in density due to changes in pressure and temperature. In a rocket engine, the gas actually produces at extremely high temperature, and as these gases pass through the nozzle, it expands rapidly and causes the density to decrease. Therefore, it is considered and treated as compressible flow inside the nozzle. And at the same time, it is also assumed to be isentropic where there is no heat transfer, considered as adiabatic, and no friction losses, which is reversible. And as these gases expand, the pressure energy is actually converted into kinetic energy, which causes the velocity to increase, while the static pressure, the temperature, and also the density all it decrease. To describe the flow condition, we usually use area-Mach number relationship, where Mach number stands for ratio of flow velocity to the local speed of sound. So Mach number usually used to determine whether the flow is supersonic, subsonic, or in choke flow condition. So let's see how area relate to Mach number in nozzle. So start with the converging section. Usually at this area, the area is reduced and the Mach number getting less than 1. So this flow is considered as subsonic. Beyond the throat, the area is starting to diverge. So we have large area and the Mach number is getting more than 1. So the flow is considered as um, supersonic. So that's why usually we use converging, diverging or D-level nozzle in rocket engine so we can achieve maximum exhaust velocity and produce high thrust.
So now, let's us move to the choke flow at the throat. Let's look at what happens at the narrower section of the converging diverging nozzle, which is at the throat itself. As the fluid accelerates through the convergent section, it reaches the minimum passage area, which is denoted here as A is equals to A star. Under proper design operating pressures, something critical will happen right at this spot, which is the flow velocity reach the local speed of sound. In fluid dynamics terms, our Mach number reach exactly m is equals to 1. When m is equals to 1 is achieved at the throat, the flow becomes choke. This means the mass flow rate through the nozzle will hit its theoretical maximum limit. Even if you continue to lower the downstream pressure, you cannot force any more mass through the nozzle, which is the mass flow rate is officially locked. So now let's move to the supersonic acceleration and expansion. So once the gas passes the throat, it will enter the widening part of the nozzle, which is the divergent section. Usually, by opening up, a pipe will slow a fluid down, but at supersonic speeds, the gas is under so much pressure that widening the pipe will actually let it expand violently, which is by converting all the heat and pressure will directly into forward speed. If you look at the equation on the slide, which is dA over A equals to m squared minus 1 times with dV over V, this is just the math proving that why this works. Once the flow goes faster than Mach number equals to 1, the middle term, which is the m squared minus 1, will become positive. That means by widening the area is the exact thing required to force all the gas to accelerate. As the gas expands and shoot out at the supersonic speeds, its temperature, pressure, and also the density will all drop significantly.
Now, let's go through the key equation that describe compressible flow in our nozzle. The first is Mach number, which is m equals v over a. This is simply the ratio of the local flow velocity to the local speed of sound, and it's the number we use throughout to tell whether the flow is subsonic, sonic, or supersonic at any point. The second equation is the speed of sound, equals the square root of k times r times t. Here, K is the ratio of specific heats, R is the specific gas constant, and T is the local static temperature. Since temperature changes as the gas moves through the nozzle, the speed of sound isn't constant. It actually drops as the gas accelerates and cools. The third set are isentropic stagnation to static relation for temperature, pressure, and density. Disconnect the stagnation properties, which are the properties the gas would have if brought to rest with no losses, to the actual static properties at any point in the nozzle, because we assume the flow is isentropic, which is no friction, no heat transfer. This relation hold everywhere along the nozzle, and they have written purely as a function of Mach number. Moving on to the next four equations. Equation 4 is the choke flow condition, which occurs when m equals to 1 at the throat. At this point, the mass flow equation shown give the mass flow equation shown as the maximum possible mass flow rate for the given chamber stagnation pressure and temperature. Equation 5 is the critical pressure ratio, P star over P naught. This tells us the pressure ratio at the throat exactly when m equals to 1. For a typical diatomic gas with K equal to 1.4, this works out to be 0.528. If the back pressure ratio drops below this value, the flow is choked. Equation 6 is the area-Mach number relation. This links the local cross-sectional area A to the throat area A star as a function of Mach number. It's the equation that explains why the nozzle has to diverge after the throat for supersonic flow. Increasing the area is what keeps accelerating the gas, unlike subsonic flow where the opposite is true. And finally, equation 7 is the mass flow rate equation under choke condition. It shows that once the flow is choked, The mass flow rate depends only on the throat area and the chamber stagnation pressure and temperature, which is nothing happening downstream can change it anymore.
Next, I will explain the nozzle exit conditions. The performance of a converging diverging nozzle depends on the relationship between the exit pressure PE and the ambient pressure PA. The ideal condition is called perfectly expanded, where PE is equal to PA. In this condition, the nozzle produces maximum thrust. When PE is greater than PA, the nozzle is underexpanded. This means the exhaust gases continue expanding after leaving the nozzle. This condition is common at high altitudes. On the other hand, when PE is less than PA, the nozzle is overexpanded. The surrounding pressure compresses the exhaust gases and may cause shock wave, which reduces the efficiency of the nozzle. Therefore, the best nozzle performance is achieved when the exit pressure is equal to ambient pressure. I will explain the engineering applications of converging diverging nozzles. First, CD nozzles are used in rocket engines. They convert thermal energy from combustion into high-velocity exhaust gases to generate thrust for launch vehicles. They are also used in spacecraft propulsion systems to produce high-velocity exhaust gases for changes in orbit and trajectory corrections while improving fuel efficiency. In satellite thrusters, CD nozzles are used for attitude control, station keeping, and raising or lowering satellite orbits. CD nozzles are also used in both solid and liquid rocket motors. Solid motors are commonly used in boosters and missiles, while liquid engines provide better control over thrust for space missions. Lastly, they are used in experimental propulsion systems by universities, research facilities, and aerospace industries to test and develop new propulsion technologies. Overall, converging diverging nozzles are important in aerospace engineering because they help accelerate gases to high velocities and generate thrust for various space applications.
In conclusion, the converging diverging nozzle accelerate airflow from subsonic to supersonic speeds through its hourglass-shaped design. Its performance is based on key compressible flow concepts such as Mach number, stagnation and static properties, isentropic flow, and choke flow. At the throat, the flow reaches Mach number 1 and creating choke flow and setting the maximum mass flow rate. Beyond the throat, the diverging section causes the supersonic flow to accelerate further. Finally, matching the exit pressure with the surrounding pressure ensures maximum efficiency, while any mismatch can create shock waves and reduce performance of the rocket engine. So that's all. Thank you. In conclusion, the converging diverging nozzle accelerate airflow from subsonic to supersonic speeds through its hourglass-shaped design. Its performance is based on key compressible flow concepts such as Mach number, stagnation, and static properties,